Here we're going to learn how to do hierarchical design in LogicWorks. Specifically, we're going to learn how to build our own custom parts. When thinking about modern microprocessors and modern digital logic circuits, sometimes microprocessors will have as many as 1 billion logic gates. 1 billion. Now, considering that the largest chip manufacturing company in the world will have a team of maybe 1,000 to 2,000 people working on such a chip that has 1,000 logic gates. Well, let's think about that. Say we have 1,000 people working on it. Divide 1 billion by 1,000. We have 1 million logic gates left for each person on average, which is just impossible to lay out by hand unless we do hierarchical design. One thing that's nice about doing digital design is that there are a lot of patterns that we can take advantage of, and because we have the patterns to follow along with, it is possible to implement more and more complicated designs with a smaller number of people. So let's try some hierarchical design in LogicWorks. Let's turn off the timing window because we're going to learn how to do hierarchical design here, and we'll go to the simulation gates library. So to start off, let's choose a Boolean algebra equation first. We can pick, say, this one here. This is an unoptimized Boolean algebra equation, but it will be sufficient to demonstrate our hierarchical design capability. So here we will paste Control V into LogicWorks, and we have our Boolean expression listed. How many input variables? 4, A, B, C, and D. How many inversions? C prime and A prime, so we need 2 inverters. Let's go ahead and lay this out. So there's no difference so far when building the circuit to test and when building the parts. 3 and 4, and then we need 2 inverted variable values. We'll take the NOT gate, place it twice, and then we'll have A and C connected. Let's label our input variables A, B, C, and D. And now we need A prime and C prime. And we should connect our inverters so the outputs are appropriately connected. We need 1, 2, 3 AND gates, 2 input ANDs, and 2, 2 and 3, and then we will have 1, 2, 3 outputs feeding a 3 input OR 3. Let's move this a little bit out and connect. So for the first AND gate, we need A ANDed with B. Next, we need C prime ANDed with D. Then we need A prime ANDed with C. And now we can go to Simulation I/O. Let's create some binary switches, A, B, C, and D respectively. And we can place a binary probe here at the output. And connect the binary switches. Now, so far we have done just about everything the same as we have in previous videos. So we can test the output of the digital logic circuit by flipping the switches for A, B, C, and D, and we can see here at the output what the value is using the binary probe. But let's say I wanted to introduce multiple copies of this circuit. So I wanted to place this maybe not just once, but 2, 3, or maybe even 10 times, or 64 times, or 1024 times. Believe it or not, placing a small structure of a few logic gates, as many as a few hundred times, is fairly common. Well, when we are creating a part, what we want to do is we want to consider that all the input variables don't come from binary probes, but they come from inputs. So these inputs need to be left as A, B, C, and D. So let's highlight the binary switches and delete them. The binary probe outputs an X. We don't need the binary probe. I'm going to use the deletion tool here to delete a little bit of wire. Now, we have 1, 2, 3, 4 input lines and 1 output line. How do we do the connections? Well, we come here to the library list and we go to connectors. Now, we can choose port in. We haven't used this in previous videos. Let's place 4 of these. I'll place one here, a second one, a third one, and a fourth one. So we have 4 inputs. Then we need an output here, so let's do a port out. Now, we have an output port, but it's facing the wrong direction. Use your arrow keys to turn it around. You can turn it by pressing the arrows up, down, left, or right. So I'm going to press the left arrow key, and now it's facing the correct direction, and I can connect the output port, the port out. This is good so far. Now we need to give each of these ports names. Each of these ports need a name. Naming tool. You must click on the middle of the X. Click here, A, enter. Click here, B, enter. What happens if you click somewhere outside and you see C? Notice that, oops, C, and then I click elsewhere. Notice that the C appeared in no man's land. It's covered by the port and it's the color black. We can try zooming in here. Let's zoom in a little bit so you can see more clearly. Control Shift E. Oops. Control Shift E. You can see that the C is behind the port and it's the color black, whereas for these two cases it was properly connected. Here, if I click the port in, the C does not highlight, so this C is not actually a label for the input port. It is actually disconnected. So we have to relabel it. Let's use the naming tool again. C, and it's to the left, so we know we got the naming correct, and then D. Finally, we need to label our output port. We'll call this, say, F. Okay, and we look at our Boolean expression. This is consistent. AB or C prime D or A prime C, all or together, and we get our output F. And we will zoom out. Once we have completed our circuit, we can save this file to disk. Save circuit, and we can place this here in our, let's create a new directory, sample circuits here. And I'll call this sample1.cct. We have saved the .cct file to we have saved the circuit to a .cct file, and we are now ready to create a part. So File, New. Now we need to go to Device Symbol. We wish to create a new device symbol. Click OK. And we can say Options. And now we want to come down to Subcircuit and Part Type. This comes off the Options menu. Subcircuit and Part Type. Click. And we want to create a subcircuit symbol and select an open circuit to attach to it, the second option. Which circuit is available? Sample1.cct. Let's click to select it, and then click OK. Once we have done that, we are now ready to say Done. Done. Notice now that we have 1, 2, 3, 4, 5 pins that appear here. And if I give a little bit more space here, take a look at the pin function. If I click on A, it's an input. I'm using the arrow keys to shift down. Input for B, input for C, input for D. F is an output. So we have 4 port ins and 1 port out. All these pins are automatically imported for you, which makes it very convenient. Now we can go to Options, and let's pick the first option, Auto Create Symbol. We have 4 input pins on the left, A, B, C, and D. We have the output pin on the right, F. Let's call the part name Sample1 instead of the default Part 1. And we want to show the pin names on the symbol. This is very, very helpful for us. Once we have done that, we can now generate the symbol. Click. And we have a symbol that is automatically generated for us. We have A, B, C, and D, and our output F. We are now ready to save it to a file. File, Save As, and I recommend that you create a new lib to store your files. So I am going to save this to a file here in sample circuits, and the library will be first lib. And now that we've created firstlib.clf, we can click Save after the part name is named appropriately. Sample1 is what we like, so save. Now we can create a new circuit. New circuit. Now we can come over to our list of libraries, go to firstlib that we created earlier, and we can pull in Sample1. For comparison, let's come back to our original circuit. Let's highlight everything except the ports. Let's bring the Boolean expression while we are at it. Control C. Oops. Now we'll continue. And now we'll come over to Circuit 2 and move Sample 1 down, and we'll say Control V. And now A, B, C, and D let's extend these 4. This is D. Let's connect it to D. C will be connected to C. B connects to B. A connects to A. Now let's pull out some binary probes. Why do we need the binary probe? We want to confirm that the output of these two circuits are the same. So we need our 4 inputs here for A, B, C, and D. Let's put in 4 binary switches. 1, 2, 3, and 4. Now let's go through all possible 16 values. We can compare these two binary probes, and if they don't deviate, we know that sample 1 is equivalent to this set of logic gates here. So 0, 1, 2, 3, 4, 5, 6, 7. Notice that we've been consistent so far, 0, 0, and 1, 1 for both of them. 8. Oops, consistent. Here. 9. 10 is consistent. 11. Still consistent. 12. Still consistent. 13. 14. And 15. Notice that both of these binary probes gave the same output. If we like, we can go now to first lib, and we can place this sample circuit as many times as we want. It's like having just another AND gate or an OR gate. It's like another simple gate. We have many simple gates in our repertoire using the standard logic gates. And if you look at simulation logic, the simulation logic library here, you'll see some more complicated circuits available, like the adder 4, adder 8, buffer 1, buffer 4, buffer 8, and so on. These are more complicated circuits that have multiple inputs and sometimes more than one output, in fact. And these are used when creating more and more complicated circuits. It's possible to put any number of logic gates into a single subcircuit, so you can create larger and larger circuits. It's even possible to create subcircuits that have subcircuits. And with this process, you can create more and more complicated designs.